would now like to turn to Chem Activity 27, in which we will introduce the background theory to interpreting acid-base titration graphs. We will examine a number of combinations, including strong acid with strong base, weak acid with strong base, and eventually weak base with strong acid. First, however, let's reflect on a relevant cartoon. I like to read it out because I think it's nicely written. Here you can see this is a World War I kind of biplane, and the caption says, "Despite the heavy flak, McAllister's aim was true, and his carefully measured aliquot of hydrochloric acid found its mark deep in the enemy's reservoir of sodium hydroxide." This is the best line. McAllister grins wryly. Finally, one of the enemy's strongest bases had been completely neutralized. As you know, we use the word neutralization in a number of ways. And one of the reasons why I highlight this cartoon is that it's important for us to be careful with this word, in the sense that for any titration we would often say the base neutralized the acid, or the acid neutralizes the base. But the important question to ask here is the pH at the equivalence point of the titration always neutral? That is it always such that the hydronium ion concentration equals the hydroxide ion concentration at 25 degrees Celsius? And of course that would be a pH equal to 7. And the answer to this question is no. When examining a titration combination, for example, strong acid with strong base or weak acid with strong base, you need to know when the equivalence point is going to be neutral and when it is not. In these series of videos, I'm going to talk you through two of the prototypical kinds of titrations. We will start with the strong acid and strong base titration. I have prepared a diagram so you can picture the experimental setup. We have here 0.1 molar sodium hydroxide in the burette. This is the titrant. The pH meter is in the analyte solution. The analyte solution is the component in the experiment that's being analyzed. What is known about the analyte is the volume of the strong acid, HCl, which is our analyte, and this volume is 20 mils. We will pipette this volume, just like in the lab, into the Erlenmeyer. We monitor the pH of the analyte solution over the course of the titration. We monitor it to see at what point do we have a drastic change in pH for a small volume addition of titrant. This will help us make an estimation of the equivalence point. Once we have an estimation of the equivalence point, we can calculate the concentration of hydrochloric acid and also determine some other properties, as you will see. Let us turn our attention to the key questions. The first question asks us to write the balanced equation for this titration reaction and also to omit any spectator ions. So who are the spectator ions? Let us be reminded that when we say 0.1 molar sodium hydroxide, there are sodium ions and hydroxide ions. We're not concerned about the sodium ions, as they do not participate in the reaction. They are therefore spectator ions. It is the hydroxide ions that are the important ions for this titration, and we know that their original concentration is 0.1 molar, as sodium hydroxide is a strong base. What about the hydrochloric acid? Hydrochloric acid is a strong acid that in water will ionize 100% to produce hydronium ions and chloride ions. Once again, we're not concerned about the chloride ions, as these are spectator ions. They do not participate in this reaction. You may have also noticed that the spectator ions, the sodium ions and the chloride ions, in this sense are equivalent to our negligible acids and bases. Therefore, the balanced equation for this particular titration reaction is 1 mole of hydronium ions plus 1 mole of hydroxide ions will produce 2 moles of H2O molecules. Does this simple equation apply to all strong acids and strong bases titrations? The answer to this question is yes, for sure. This is because all strong acids will have negligible conjugate bases, and all strong bases will have negligible conjugate acids. Therefore, there will always be these spectator ions that we do not need to include in this balanced equation. This is the only thing that's ever going on for this kind of strong acid, strong base titration. The idea of doing this kind of titration, however, with a pH meter is that rather than use an indicator to estimate the equivalence point, we will monitor the change in pH. Our goal is to find the point where there is a drastic change in pH with a small addition of titrant. And more specifically, we're going to find that point which is halfway along the drastic change in pH. I'll say more about that in a minute. The drastic change in pH on our graphs can be seen here. It is a little idealized in that in the lab, this very straight line would be hard to achieve. Halfway between this red line that I'm highlighting and this other red line that I'm now highlighting, halfway between these two lines would essentially be right here. This is our estimation of the pH at the equivalence point, and in this case appears to be very close or equal to 7. Is this what we would expect for a strong acid, strong base titration? Well, the balanced equation tells us that the only species present at the equivalence point would be water and, not shown in this equation, any spectator ions. That is the negligible acid, sodium ion, and the negligible base, chloride ion. Therefore, we would indeed expect a neutral pH, which is, of course, 7 at 25 degrees Celsius. A titration reaction between a strong acid and strong base is therefore a neutralization reaction in the true sense of the word, because the resulting solution is indeed neutral. We also need to consider the volume of titrant that corresponds to this drastic change in pH, and specifically the midway point that corresponds to our neutral pH. This is for two reasons. For one, a point in 2 dimensions requires 2 locants, that is both the pH and the volume of titrant. Secondly, and perhaps more importantly, this volume of titrant is used in subsequent calculations. In this case, the estimated volume of titrant at the equivalence point is 25 mils. In the key question number 2, we are asked to list on the pH graph the predominant species in the Erlenmeyer before the titration starts and at the equivalence point. Hopefully, based on the earlier discussion in this video, the predominant species at these different points is fairly obvious. Before the titration starts, an aqueous HCl solution gives rise to hydronium ions, and the spectator ion, chloride ions, and given that the titration occurs in a water solvent, a whole bunch of water molecules. To be clear, the chloride ions are still considered to be predominant, not because they influence the pH or participate in the titration reaction, but because there are a substantial number of them. There's a substantial concentration of chloride ions. Also, because the water solvent is ubiquitous, we tend not to list it here as a predominant species, as it is always a predominant species. At the equivalence point, we have the spectator sodium and chloride ions, and again, a whole bunch of water molecules. It is worth pointing out that in doing this kind of titration, in order to visualize the drastic change in pH, we collect data past the equivalence point. At this point in the process, where we're past the equivalence point and where the graph levels off at very high pH values, there is an excess of hydroxide ions, along with the spectator sodium ions. Let us review some stoichiometry in the context of this kind of titration. This corresponds to the key question number 3. I start with our balanced equation. Consider what we know about the hydroxide ion solution. We know its concentration to be equal to 0.100 molar. And from the titration graph, we have estimated the volume of the titrant at the equivalence point to be 25.0 mils, or 0.0250 liters. Now let us consider what we know about the hydronium ion solution. Given is the original volume of the HCl solution, which is of course the source of hydronium ions, and this is equal to 20.0 mils, or 0.0200 liters. What we don't know, but can now calculate, is the original concentration of the hydronium or HCl solution before the titration. The calculation would look like this: 0.100 molar hydroxide ions times the volume, 0.0250 liters, will give us the moles of hydroxide ions. This is multiplied by 1 mole of hydronium ion divided by 1 mole of hydroxide ion. This comes from the balanced equation, which will give us the moles of hydronium ion. Finally, this is divided by the volume of the hydronium ion solution, the original volume, which is 0.0200 liters. And this will give us the original concentration of the hydronium ions, and correspondingly the HCl. You can see that this is equal to 0.125 molar. This is a typical stoichiometry calculation, such as what we saw in first semester of our first year course. In the next video, we will look at titrations involving a weak acid with a strong base.